Good.
Mhm.
All right. Let's see if that still works. It does not. All right, so that's can't really see it too well, but that's how we got it. Looks all cool and sleek and lights on and flying real well. After we tested it for a month, that's how it looked. As you can imagine, those arms probably aren't supposed to dangle like that. The propellers are supposed to be intact. And while that may look like it's a bad thing, ultimately it's a good thing because we, one, found out how hard it could be flown and found its parameters of use. And two, we said, okay, that is better than what is currently used because the other ones were failing twice as fast or even worse. Another test that I participated on was the Joint Assault Bridge. That was tested out at Fort Riley, Kansas and Fort Hood, Texas. This guy is meant to bridge short gaps, whether they're just gaps over a ditch that's filled with water or nothing. And it's put on a Abrams chassis, main battle tank chassis. And one of the crazy things is those tanks are really heavy. The current ones are running around 80 tons. And when that bridge is fully extended, due to the statics and dynamics of it, that tank will actually start to lift off the ground. It's kind of scary when you see that happening. Yeah. All right, so I was only there for about a year and a half. What did I learn? I learned how to interface with DoD customers, which turned out to be really handy in my next job. I learned how to navigate the government bureaucracy, which if any of you have ever worked in any form of government, whether it's city or federal, it's a pain and it takes a lot of know-how and skill. And then I met my cousin, Dr. Dave, on a business trip that I had no idea I was related to, but he's my fifth cousin, 4 times removed. And did I mess it up? I did. Gotta love this. All right, and why did I leave? Ultimately, my heart wasn't in the work. It just wasn't being fulfilled in my career, I didn't feel like. The location was less than ideal. It's an hour north of Austin, but that's about it. There was not much for us to do there after work. And then the travel requirement was too intense. So if someone tells you that the travel is going to be a quarter of the time, that's going to be stressful if you're a newlywed and you're away from your family. That's not advisable. I think when I was gone for a month one time, within the last week of me being gone, one of my dogs became paralyzed and my wife got shingles. So it just was, I took that as a reason to leave. So I ended up getting a job with the NASA Marshall Space Flight Center. It's located in Huntsville, Alabama. If you've ever been to Huntsville, Alabama, you'll know that it's not like the rest of Alabama or what you may think of Alabama. It was founded in 1960. It was transferred over from the Army. It was the Army's ballistic missile agency. Then when NASA was formed, they took some assets and transferred over to the new agency. Out there, their expertise is in propulsion, additive manufacturing, launch vehicle development, testing, and one of the cool things that they actually do is they operate and maintain all the payloads that are on the International Space Station. So once the astronauts are on board, they're doing all their science experiments and whatnot. The station, there's a control center right there that manages all those science experiments that are going on. And they do everything all the way down to tracking down where the screwdriver is. So right now, actually, I'm going to take a drink. Right now, I work in what's called the environmental test facility. Sorry, I'm trying to stay in range for the camera right here. I work for the environmental test facility. And what that is there's a couple different things that they do there, but the main thing that they try to do is they try to simulate the environment of space so that we can test things on the ground before they're up there. So on your left, we have what's called V20, and that's actually a former liquid oxygen tank off of a Saturn V, which is the moon rocket, that was turned into a vacuum chamber that's 20 feet wide and about 20 feet long. So I knew you could park a truck in there and call it good. And that's pulled down to a vacuum of, we call it, we refer to everything in the 10 to the minus, and it goes down to 10 to the minus 5 torr, which is roughly, sorry, I had the number worked out before I came here. I want to say it's like 1/10,000th of a percent of an atmosphere. I may be off by a couple zeros, but after a point, it doesn't really matter to our brains. Currently, that chamber is being retrofitted to test Martian and lunar regolith. That stuff is kind of very hazardous to work with because it'll aerosolize, and then when you inhale it, it's made of silica and it's very sharp and it's in your lungs forever. And a lot of the people that are working with it don't want that for some reason. And the chamber on the right, that is V16, that is the chamber that I am the facility manager of. And I am setting up a test for the DoD. It's a joint Air Force and Navy test. It's for an air-to-air missile. And it'll be tested at rapid ascent and descent, so essentially raising the pressure and lowering the pressure really quickly. And then it'll be tested in thermal vacuum, so extreme temperatures at vacuum, both high and low. And that one is very, I'm building it up. This one was originally 2 separate chambers that were sort of put together, and now it's being set up to do things that have actually never been done in the facility before. The rapid descent, rapid descent, the pressurization, the facility hasn't ever been set up for that, so I'm kind of breaking ground and writing procedures for it. And this one is the OUT test chamber. OUT stands for Orion Urine Test. So I am a pee tester. If you had told me that 10 years ago, I would have said, you're crazy. Why would I ever test pee? And there is one worse job than it. I'm not going to go into detail, but so the reason that we're testing urine in this chamber is on the Orion space craft, which is a capsule that's going on top of SLS, and it's what the astronauts riding on a NASA rocket will be riding on. It has a urine system. However, if that urine system goes down and there is no backup, that is a loss of mission. They have to call it right there and get home immediately. So what we are doing is we're testing a contingency system that will, instead of keeping the urine and recycling it, it's just going to vent it straight to space instead of keeping it and turning it into drinkable water again. This is actually being done for the Johnson Space Center, which is out in Houston, Texas. They have the facilities to technically do this. However, they didn't want to deal with having to clean up pee. Which, again, understandable. But we had 2 big chambers that were not being used. And our branch chief, my boss, said, sure, we like money. So we took this big chamber that was sitting unused for probably 2-3 decades. And we grabbed that chamber, which was, I think it came to us like from the DEA or ATF because they didn't want it. And it was actually meant for testing explosions. But instead we're pulling it the other way and we're pulling a vacuum instead of pressurizing. We connected them together through a series of piping and through a couple of conditioners in there for so we bring down the temp or the pressure, we bring down the temperature so that all the urine that gets in there either vaporizes or it solidifies, so that we keep as much out of the actual facility lines as possible. We don't want to bring it into our pumps and anything like that. So we use this to test urine, and I actually do have a video of a test, which see if I can we close these real quick? Just so,
Yeah, so those are broken. Or
oh, so we're not closing those. Let's see what we can see though. So that is the orifice that it will be injected into space or ejected into space. And that's the water flow. What's happening right here is it's freezing on a wall that you can't see. And as the water hits it, it just freezes. And honestly, there's some things that I don't even quite understand what's going on, because you get into that, well, I'll go into it a little bit further on next slide, but I just admire the beauty of, okay, this one isn't pee, this is water, but I probably had you going for a little while. It's actually a slightly more yellow, not very though, like, so we don't want this to happen. We don't want it to actually make contact with the orifice up there. There's a couple of heaters on there to try to prevent as much icing as possible. But once it does, it starts doing some really weird things. Pay attention over there. Some of the water will actually start to spurt out. And if you can tell me what's going on, this is in slow-mo. Yeah, this is in slow motion. It gets real weird. But yeah, so that's more or less what a test looks like when it's not going well. So this is, I'm sure any of you that have done chemistry have seen this. This is the phase diagram for water. We're operating roughly around here. Did I go too far? I went too far. All right, so that's where we're operating, that red box right there. Our temperature is between -65 and +65 Fahrenheit. And our pressure is between 20 millitorr and 700 millitorr. I'm sorry for the units. Unfortunately, we still use those. So as you can see, there's both the possibility of solid and gas. However, liquid doesn't start until way, way higher. But there was obviously some liquid in there. I have no idea what's going on. So if anyone has an idea, that'd be cool. But I've kind of relegated that and let that haunt me at night instead of devoting work time for it. So I'm just going to leave it on this for a moment because Mars is cool. So if you noticed, like some of those facilities look like they're kind of janky, right? Like they're kind of thrown together, which on the surface looks bad, but and how many of the facilities that you guys use for any of your projects are kind of janky? It doesn't matter what I was told that the customer doesn't care about the state-of-the-art equipment. They care about the quality of the data. So if janky means that you can throw it together quickly and give them data within a month, that's better than having something that looks really, really nice. So I just want to kind of dispel the myth that once you get out of here and go to industry that everything's nice and shiny and brand new. It's not, but that doesn't matter. You work with what you have. So I'm gonna sort of switch into a different topic that I worked on. This is a brief summary of the robotic Martian exploration. Starting about what 1964, we've had close to 24 orbiters, just satellites that orbit the surface and collect data. We've had half a dozen landers and then another half a dozen rovers. So our track record, we've had 22 total spacecraft go there, 17 successes, 5 failures. However, within the last 2 decades, everything that NASA has sent has made it and completed its mission, if not more. This right here is just a picture of Perseverance, the most recent rover to land on Mars, and that's its sky crane and the vehicle itself. So we sent all these things there. However, we've never gotten anything back. The only Martian things that we have on planet Earth are meteors that have landed, meteorites that have landed and contain some Martian soil. So about, I don't know, as early as the 60s, they started planning for a Martian sample return. And that's part of what I worked on over the last year. So the current architecture of the Martian sample return, we just sent Perseverance, which is actually collecting samples out there. It has a drill on it that'll core rocks. It'll put them into titanium tubes, and it'll just, and the actual engineers, this is the language that they use in their meetings. They say it'll just poop them out and leave them right there. So it'll put the samples in tubes. Then we're going to send another vehicle. It's called the Earth Return Orbiter, and that'll be just orbiting Mars for a long, long time until we send something again. And it's changed a little bit. So one sec. Recently, this part, sample retrieval lander, has changed to be dual mission architect. So it's architecture. So we originally planned on sending the little retrieval rover with the Mars Ascent vehicle, but however, now they are separate missions. So we're going to send the sample retrieval lander rover. There's a lot of acronyms. So we're going to send a little rover to go collect those and bring them to another thing that's going to land down called the Mars Ascent vehicle. And that's what I worked on. I worked on the Mars Ascent vehicle. And then the little rover is going to load them into the Mars Ascent vehicle. The Mars Ascent vehicle is going to go up to space around Mars. Actually, it's not. It's just going to hit Martian orbit. Most of the vehicle will fall back to Mars. And then it'll rendezvous with the ERO, the Earth Return Orbiter, and then that'll come back to Earth. I know it's a, you can ask questions all you want after. And then we get to study Martian soil on Earth. So this is the evolution of the Mars Ascent vehicle. The preliminary concepts, they've evolved since the 1960s, 70s to varying levels. They've been studied, they've been canceled, it's always been on the back burner until we actually had samples that have started to be collected on Mars. The current concept was developed over the last 25 years. It used to be in the hands of JPL solely, the Jet Propulsion Laboratory down in Pasadena, California. However, back in 2017, they contracted the project out to the Marshall Space Flight Center. And this is how it's evolved since then. It started as when we took it over, it was a hybrid rocket, which, without going into too much detail, you have a solid fuel and a gaseous or liquid oxidizer. So there's some benefits to that. You can, again, ask questions later if you want explanation on that, but that's a lot of detail. But now it is currently a solid rocket for both. So it's kind of like a rubbery material. So the current MAV architecture. So this is the MAV standing upright, and that is a 6-foot tall person. So it's not a very big rocket. I mean, it's the biggest rocket that I've ever worked on, but it's still not a very big rocket. And its current architecture, it's a solid, guided, unguided rocket, SSGU, meaning that the first stage is just a solid, the second stage is just a solid, and the first stage is guided, meaning that it can actually maneuver itself, and the second stage is unguided. So once that rocket lights, it's going in that direction. Let's see. So the way that it gets its movement on the bottom, it does thrust vector control. So it just moves the nozzle around with electromechanical. All the big rockets, they use hydraulics and much more industrial mechanisms of getting their control. However, this is smaller, it's lighter, and it only needs to work once, and it's not human critical. So this is the first stage right here. You have the rocket motor itself, the inner stage right here. Second stage, another rocket motor, like a smaller inner stage, essentially. And then here's the payload. This is the actual payload right here. and that's where the sample tubes are going to be contained. The whole thing is approximately 3 meters long, 50 centimeters wide. Don't quote me on those numbers because this thing is changing all the time. I think it's actually gotten a little bit more rotund lately. I think it's maybe 54 centimeters wide now. So this is what the ascent mission looks like. It's going to burn its first stage for about 78 seconds. Then it's going to coast for another, 6 minutes. And then it will finally get into where it needs to spin up and burn the second stage. And then it'll spin down so that it actually can be captured. And the orbital sample will be released and essentially thrown into an orbit. Then over the course of the next few days, the Earth Return Orbiter will change its orbit so that it'll match the sample and actually just catch it. So it's launched by what's called the Vector Launch System. It'll go through what Max Q. If you ever watch a SpaceX launch, like you'll hear them talk about Max Q. It's the moment where if it's going to fail, it's going to fail there, at least structurally. That's when it's undergoing all its high accelerations, all the forces that it's going to hit. Because rockets are real strong in this direction, but they do not like any wiggling about their body, I guess. Yeah, let's see. Again, this is a concept. It's not permanent in any respect. So there's some unique challenges that come with MAV. It's never been done before. We've never launched a rocket from another planet. I guess we launched a rocket from the moon, but let's just say planets are cooler. However, we've never launched one that is completely remote. So the Martian environment is completely different than the surface of the moon. It's remote. It'll be there for 2 years or so before it actually launches. The temperature swings from low negatives, like I should know the numbers. I probably did at one point. But it swings from low temperatures to high temperatures. The atmosphere, it's at roughly 1% of the atmosphere of Earth. So you're going to be off-gassing a lot of things. So if you had any oil lubricants on there, they're not going to be there by the time you launch because they're going to essentially all evaporate. It has to deal with a lot of radiation because Mars does not have a similar magnetic field to us. So any of the radiation coming from the sun, even though it's going to be roughly a fourth less because of its distance, it's going to be feeling the full force of it for 2 years. And then dust. Whenever a dust storm gets kicked up, it's going to get dust everywhere. And it's not really going to leave very easily. Another challenge is MAV is a payload itself before it's actually launched. So before this mission actually starts, it's already been on, it has to get from our surface to atmosphere to orbit, which is already a risky situation. It has to travel in a transfer orbit to Mars, which less risky, but still risk. And then it has to go through arguably the most risky part, which is landing on Mars. And that's usually where we lose spacecraft if we're going to lose them. And that's all before this mission even gets started. And then you have to deal with the orbit window of Earth, Mars, and then the orbits of the two spacecraft that have to interact with each other. So the overall MAV design. This is just a little bit more of a broken down. So this is the thrust vector control right here. As you can see, this is the split. So this is cut in half. Like I said, most of the time it's controlled by a hydraulic system. However, this is being controlled by electronic mechanisms. What it is this is kind of like a ball joint. So it just sort of slips and moves the thrust vector. You have the points where the vehicle is, the MAV is going to connect to the lander. It's called the Vector Launch Mechanism Attachment Points. And then the second stage is has a hydrazine, sorry, the first stage has a hydrazine reaction control thruster. So that's where it gets some of its guidance from as well. Hydrazine, we're trying to get away from hydrazine. That was actually one of my projects when I was interning, was working on alternatives to that. But it works really well, and we know it like the back of our hand. And we have to make sure that doesn't freeze while it's on Mars. So that's actually going to have heaters on it that are constantly keeping it warm so it doesn't freeze up and blow our lines. Then we have our separation system, which they're made of non-explosive actuators. So actually what they're bolts that are tightened down with some washers that sort of spring. And then the nut on the bolt will decouple and it'll spring out and separate. And then that little box right there, that contains little spin and de-spin motors, which in rough strokes, they're kind of like the SD's model rocket motors. They just burn in one direction, spin it up. Then when that part of the mission is done, they'll burn again and spin back and de-spin. So another thing that will be done with this is we're testing it on Earth as much as we can. So we're doing a flight test, which will be done out of Walvis Flight Facility out in Virginia. They launch a lot of smaller sounding rockets, and that long rocket up there, that's a two-stage rocket that's called the Terrier Black Ram. Obviously, they just throw the names together. Very creative. And that's going to launch, and it's going to separate, and then our mission starts, and we get to test the second stage only. We have a first stage simulator set up here just for mass, and so that we can test the actual separation. It contains a couple other things on it, but mostly it's all simulation. So with this, we'll be able to prove that our systems are working and that more or less the concepts are good. This will get us up to an altitude that is very similar to what we're going to experience in Mars, both in temperature and not temperature, but mostly pressure. Pressure is the real big one that we want to test. There's some trades that are done with this. Like we have to consider, do we chill it down to negative something before we put it on a rocket? And then you have to consider, well, how long does it take to get from a chiller onto a rocket? And this is a live rocket. How do you deal with a live rocket? No one wants to deal with a live rocket. It's a lot more complicated than it sounds. Even just the simple things on, do you make it realistic or not? So this right here, this, again, like I said earlier, they changed the architecture of the mission from having the little rover guy on top to that's going to be on its own little mission now. So this is dated. However, I don't know how much they're going to change. They may change a lot. They may change a little. So yeah, right there you have the sample return rover. And this actually looks very similar to what the, if you ever see like the, 7 Minutes of Terror video that JPL put out, it kind of looks like the very top of the sky crane, because it's essentially doing the same thing minus one big major part. You got 2 small thrusters right here. Well, I think you have 8 total, but they're essentially just using propulsion. They'll wait toward the end. This is what it's going to look like when it's in its begin state. The top one is what it's going to look like when it's in the beginning of its EDL sequence, the entry, descent, and landing sequence. That is a heat shield on the bottom, and then on top it's actually a solar array for when it's in travel. So Mars has an atmosphere that's, what do they say? They say it's thin enough to not matter, but thick enough to like ruin your day. Like it's thin enough to not help you, but thick enough to ruin your day. Like it doesn't break, it doesn't apply the brakes enough, but it'll heat your spacecraft up too much that you'll lose the mission. And then, so that's where the MAV actually sits in there. It's encapsulated. I can go back and forth, so it's kind of a cool little. Again, this is outdated since it's no longer on there, but that's what it was supposed to look like when it landed. And actually, you can kind of see the mechanism how the rover gets off. It sort of just flips down on that arm that lands there and just plops it on down. You got 2 solar panels so that you can power all the auxiliary systems, heaters, computers. And then you have the vector launch mechanism. There were a couple trade studies on how to launch the vehicle. Originally, they were planning on just having it kind of pop up like this and launch like a bottle rocket, like a normal bottle rocket. And then they realized that there were some issues with the mechanism and dust. So they decided to be like me when I was a teenage boy and took the bottle rocket and just threw it up in the air and let it go off and hopefully not hit my neighbor's wood shingle house and burn it down. Never happened. So I'll just show you the graphic. It really caught me by surprise when I first saw it. So it literally just pops it up and it lights the rocket right there. Seems very uncontrolled, but that's what the geniuses at JPL are wanting us to do. It's called the vertically ejected controlled tip-off brake mechanism. I think they forced that one into it. So what's the point? The point of the mission is to get soil back, 500 milligrams of it, which is a pound, to be able to study it on Earth. And you might think, why not just send the instruments there to study it? Aren't we already doing that? We are. However, that's limited. When you think about it, the 2 rovers that we sent recently, they have maybe a total of 24 main instruments. However, if we bring 1 pound back, we can study on every single instrument that we have here, instruments that weigh several tons that are far more advanced than the ones that we sent to Mars. So you're ultimately saving a bunch of missions. If this one's taking 4 launches just to get this 1 pound back, you're getting your investment back. I'm not even going to say how much, but it's an insane amount that you get back. 55 important future scientific investigations related to the exploration of Mars were identified back about 2 decades ago, and half of those were categorized to be able to be solved by bringing back 1 sample return. Ultimately, all this goes to further human space exploration of Mars and the rest of our solar system. So looking to the future, we have Perseverance that landed back in February. We have first MAV test flight soon. MAV launch from Earth, a dozen or so Marvel movies from now. MAV arrival 18 months after. MAV launch another year after that. Martian sample return to Earth during the next Hohmann transfer, which is just an ideal time to transfer. And then a crewed mission, hopefully by the 2040s. Those are vague just because people get mad when dates change. So give or take 1 or 2 movies. So I'll hold this since this isn't really applicable to the rest of the audience. I can do this in the Q&A. Again, I'm running close on time, so I just want to leave time for the Q&A. Applied internships, 2 different kinds of internships. Huntsville's great. I can do a sales pitch for you later. Here's my contact information. There's me eating pizza. And I'm literally a rocket scientist. It's kind of fun to say that. So, questions?
Yeah.
Oh, yeah.
I'll monitor the online questions that come in. All right.
What's up?
One question. You mentioned like a number of different projects you've been involved with
Mhm.
in this, presentation. How many projects say you're currently involved with?
So he asked, how many projects am I currently involved with? I'm currently involved with the Orion urine test. That's actually being tested. What time is it over there? Yeah, it's being tested right now. I'm currently involved in all the ones, the vacuum chambers. Those are my current projects that I'm working on. So three main ones that I'm working on right now.
How much of the Russia blowing up that satellite, jeopardizing all the launches and satellites up there now. Do you have any idea?
I have no idea. I just read a highlight while I'm on vacation, so I try not to do too much work when I'm not working.
I have a question. So I know you mentioned that you work for DoD and getting projects with the U.S. Army. So why did you decide to work for NASA versus working for a military contract company like Lockheed, Raytheon, or Northrop?
So why did I want to work for NASA
Yeah, versus those military contracts.
versus military contractors? So I kind of had an ethical dilemma of working for the military and building things that ultimately kill people. Though not everything does, it goes, the ethics of it. That was one major thing. And two, I feel like if there is a branch of government that most people like, it's NASA or the Forest Service. Those two are the two that are near and dear to my heart. And because I think space is ultimately one of the few industries that the government is involved with that really progresses the future. And it trickles on back. There's plenty of reasons, but those are like the main ones that I would say. Got anything for me here now?
No, for some reason, I'm not able to access the chat.
You can take the PowerPoint down if that
Okay.
helps.
It's okay, so we'll stop sharing. And then,
Anyone out here?
any other questions here?
Anything, whether it's about my work, my education?
Sure, when you started your internship, your first one.
Yeah.
Was it your plan, to end up in NASA or to end up with government working, I guess?
So it wasn't my plan to get to NASA.
Yeah.
When I got the internship, it was sheer dumb luck. Like, I'm not gonna try to say that like I deserved it more than the person sitting next to me. I was telling someone earlier that I got I got a workshop for a week. The guy who hired me as an intern saw that I had a workshop with NASA and he said, that's more or less why I hired you. My job with the Army, they said, oh, well, you were able to speak so intelligently to your internship work in your testing. That's why we hired you. And then, oh, you did a lot of testing for the DoD and as a full civil servant already. That's why we're hiring you at NASA. That's honestly like, it just takes one small thing to get there. I know that's not exactly what you asked, so I will answer that question. It was not my plan. And I once told one of my teachers, hey, I want to be an astronaut. I know that's stupid, but why not set a high goal? And I made efforts to go in that direction. Did I ever think that this was a sure thing? No, I never did. But I actually made a concerted effort toward that direction. Hope that answers it.
It does.
Good.
If you don't mind me,
Yeah.
ask a follow-up question. So how did you first get that workshop? What got you in that direction?
So how did I first get that workshop? What was it? I saw that there was going to be an educational, essentially a talk about this program at Reedley College. And I was actually I actually transferred over to Fresno at that point. However, I was still taking one class at Reedley. So I was eligible for that program because I was taking that one class at Reedley and I took that program. So I just heard about it being there. And I go to these things. Like essentially that's all I can say to find things. Yeah. Yeah, absolutely. Did you have a?
You said you were like the, I can't remember if it was project manager of vacuum or if it was like the facility manager.
Facility manager, yes, I manage the facility of a vacuum.
Okay, in that, does that job entail more like testing and like analysis and design, or is it more you managing what everyone else is doing?
So that one, that one is a lot of managing, sorry, it's the first one. I'm trying to think of how you worded that.
Oh, like testing.
Yeah,
and
it's
analyzing.
testing. I'm writing up the test plan. I'm saying, okay, we need to have a relief valve go in here. We need to bring in high pressure air through this line so that we can hit the parameters that the customer has set forth for us, and things like that. So it's a very, I hesitate to say technical because you're not using that book that Sophia has right there, but you're still doing technical things. Yeah, it's not just managerial, though there is some of that. Got anything from Aaron on?
They're asking technical questions about
Okay.
the presentation
Oh.
itself, but, yeah. Nothing over here, no.
Okay.
From the audience, anybody else, any other questions? Oh,
What would you say for someone who does not yet have a foot in the door with NASA or any other aerospace company, who's trying to graduate in the spring? So, as far as I'm aware, companies are reluctant to take on interns who aren't students, but also reluctant to take on full-times without internships.
So use every advantage you have. So like I was not the student that program was set up for. The NCAS program that I was in, it was meant for freshmen trying to figure out what they want to do and keep them engaged in school. However, ethics aside, I took it and because I qualified for it, and I was able to use that to my advantage later on. So at your point in your career, go to conferences. If you're not going to SHIP, SWE, SACE, NSBE, go this year. Where you plan on going?
I went last week.
Okay, well, go to, are there any more coming up?
Oh, NSB's coming up. in
NSBE.
March.
Go to NSBE.
Yeah.
Go to NSBE, get a part-time job working at a CNC shop. And something like that, honestly, like anything like that can show that you have the hands-on. Employers love tests. So if you can show that you're testing something or that you're building something, that'll be able to help you a whole bunch.
okay.
So yeah, and CNC shop, agricultural place, mechanic, anything like that. Like you'd be surprised at how many people that I've met from Georgia Tech or MIT that have never touched a wrench. And that it shows and it's helpful, to be the one to know how to actually fabricate something.
Okay, we do have a question from online. It says, what was the most beneficial course taken that you took at Fresno State as an undergrad?
You know,
Um,
I was told to prepare for that question. So I actually, to piggyback off that, I would say the course, I forget whether it's actually a 159, ME 159, when you're actually in the shop using the lathe and mill. Maybe not, I forget it.
I mean, 95.
95, there we go, ME 95. That one, again, to be able to have technical and hands-on experience, that is the thing that will make you I guess it's a double threat, not a triple threat, but I would say that's the most beneficial one, unique to Fresno State. Other than that, it really just matters on what you go into. There's no course that will prepare you for test. That's something that you just more or less get from life. Got another?
Yeah, one more. It says, some advice for someone looking into to get into the military technology industry.
So that one is just apply. So I was telling a student earlier, if you cast a narrow net and only apply to 3 places because those are the 3 places that you want to get into, you're going to be disappointed because odds are you're not going to get them. However, if you cast a wide net and you apply to every single thing that even seems relevant to you, you're going to get success there, and then you can move toward and make a concerted effort toward where you want to go. So yeah, I hope that answer your question. I hope.
Any other questions? Oh, yep.
Do you have any previous experience before you got your first internship with NASA?
Other than that, 1 week thing down in JPL, no. At least directly space related. I grew up in a farming family, so I fixed things. I know I'm hankering back to that one again, but that is one of those things. If you just explore things that are around you, you'll get a better understanding, be able to apply it. So that urine test, the first day of test, we had issues. Our peristaltic pump died. And while the other engineer was trying to figure out, where can we get another peristaltic pump? I just went into the junk room, grabbed a piece of flexible tubing and made a siphon, which just uses the difference in height and delta P, and you can literal delta P. And I saved a day of test over having to source another peristaltic pump. And another one was that ice bridge that you saw. That was not what we wanted, and that was happening during test. What do? Okay, we could throw some heaters on the back. We could try to vent and like heat thaw it down. I said, what if we just hit it with a stick? So we found like a bearing that went through that can withstand vacuum. Put that in there and had a technician make a stick that just, when you rotate it, it hit the bridge and it knocked it off. And again, we saved test. Small things like that. So those are the things. I hope I answered it. Again, I'm sorry if I ramble. Did that answer at least in some respect, or at least answer a question you didn't know you had? Okay, yeah. Become useful.
Any other questions from the online audience? How about here? Anybody here in person? Anything else you'd like to know?
Out of curiosity, up crossing, I feel like you probably did tell us where your first internship was, but I did.
Who's that, Marshall?
Marshall, okay, I was just curious, what was like the first internship? you did?
So the first internship I did was working with green propulsion, green monopropellants. So essentially alternatives to hydrazine, because hydrazine is toxic, carcinogenic. It has some good qualities, but those are the two main ones that make it an issue. Meaning that you can't use it in a lab like Jordan without extreme safety precaution. And it's also much more expensive to use on a spacecraft, even though the material itself is dirt cheap. Once you add something that has a bunch of restrictions to it, you increase the mission by $1 million. And if you're just looking for like a secondary, if you're a secondary payload and you want to get onto a primary payload and they aren't using hydrazine already, they're not going to take you. So yeah, that's what I did.
Okay. Anything else? Anybody else? Any additional questions? All right. No one from the online audience has any other questions?
Again, if you have any questions, that's my email address. Some people know I don't respond very well. I'm sorry or not. But I will make an effort if I see, put Fresno State on there and I will answer it within a day.
Okay. So yeah, thank you. Well, thank you, everybody. Thank you for being here. Thank you, Austin. We do have a little token of appreciation for you. Thank you so much for some things from Fresno State. Thank you so much for making the trip out here and for joining us this afternoon. Let's give Austin a hand, please. Thank you so much. Have a great afternoon. For those of you that are here, we still have plenty of food. Help yourself to some more food, okay? And to the online audience, thank you so much for being with us this afternoon.
If you have any more questions, I'm still here.
Do you know of like a reason why they choose for that return method?